So I guess before we just get started, how many people here are interested in kind of a distributed system approach to this? All right. So a lot of this is on the design of the broker to use MQTT as the protocol. Now, I don't have a lot of distributed system content on here, but what I can do, having done a system very similar, using a lot of the same content, I can actually weave some of that in if you're interested. So don't be afraid to ask questions. Hey, how would you do X, Y, and Z by extending this, okay? So don't be shy about going further. I'll try and take those questions as they come. I'll do my best. I'll answer based on the knowledge we share here, the knowledge from that other system, and if some of it goes too far, I don't mind saying I got no idea, but I can try and look it up for you. Does that sound reasonable? Good. All right. Let's see if I can get this going. All right. Are you ready? Cool. All right. So I'm John Dubchak. I work at Castlight Health. Might as well advance the slide, I guess. So I'm new with this clicker, so give me some time with it. Oh, it's not working on me already. Let's try it again. Here we go. There we go. So our agenda today, typical, right? First thing you want to do is shameless self-promotion. And then I'm going to give you a little overview of messaging. How many here are familiar with messaging systems in the enterprise? Just what kind of systems are we familiar with? Anyone?
Rabbit.
Pardon me?
Rabbit.
Rabbit MQ? Okay. Self-made system. Yeah, there's a lot of those in the enterprise. Zero MQ. JMS, I heard. Yep. That's funny thing. You'll see a little bit of concepts from JMS in here as well. A lot of that is my background as well. So we're going to talk a little bit about basic messaging concepts regardless of what system you've worked in, whether it be homegrown, RabbitMQ, ZeroMQ, JMS, or any of them. They all fundamentally talk about the same things. And with enterprise messaging, the scale is larger, the challenges are bigger, but essentially the same fundamentals underlie all of that as well. So with the MQTT messaging protocol, we're going to get into designing and implementing a broker, kind of the challenges I faced and where it came from. And what's interesting about that is I was at C++ Now back in May. Was anybody there that's in the room? Nobody, good. Anybody an MQTT expert? Excellent. So everything I tell you, except for this guy here, is the straight up truth. Believe me. Take it at gospel truth. So at CppCon, they call it as well, in May, I sat through a presentation with Michael Case presenting on his MQTT client. I hadn't really used MQTT. I'd used RabbitMQ and ActiveMQ and some of the other larger ones, WebSphere, and for basic messaging and messaging systems. The thing about enterprise messaging, right? If you're actually talking about the low-level messaging protocol as a developer, I think you're doing something wrong because you're actually talking about fundamental things that should be abstracted away from application level concerns. Kind of my opinion. But anyways, what Michael presented was a really interesting client design and implementation on what they had done for a kind of a glass sorting machine. And so I thought, I really hadn't had much experience with MQTT, so I thought, here's a great opportunity for me to try and sit down with what he said was a lightweight protocol, something that was reasonably easy to to use, and maybe I could design a broker around that based on, like I said, an earlier REST server that I had written that worked across a number of machines, sharing work and distributed work as well. And I thought, well, I'll give it a shot. So this is kind of the work product of that irrational decision at the time. So a little bit about me. Been doing C++, I want to say since, well, my first encounter with C++ was back in '91 and reading a chapter of a book. The book was on C. There was a chapter on C++, and it started with templates. And you can guess how that went. And so I didn't really do much with it until about '95 when I picked up more information really on just how to do regular C++ versus C with classes. And I stuck with it and started professionally programming about '97 with C++. And been going to the conferences that have been being offered since about, I think it was 2000 or 2001. I believe it was 2000. The first conference I attended was in Boston. And I ended up sitting beside Eric Nibler for the week. And that was right around the time that Andre's book on modern C++ design, which I had in my hand and brought with me. And I asked Andre to sign it, hey, sign it for me. He was a guru, rock star at the time. And I was just this little guy trying to learn all this stuff. And you can tell with Eric's career, where it's gone, the trajectory in mine, that it wasn't the Boston water. So, messaging overview. So what is messaging? My definition of messaging is abstract, right? The communication of data from a sender to receiver over a given messaging channel in agreed upon format of exchange. Now what's key here, sorry, we missed one. It's communication, right? We can all agree with that. It's data. We have a sender. We have a receiver. There's a channel. It's an agreed upon format, and we're having an exchange. Now, what's interesting about that, and I'm not going to say too much about it because most of us have messaging experience, is these, to me, represent the domain of interest when designing a messaging system. And to me, the canonical messaging model is basically client-server, right? Request and response. And that's what really MQTT is built around, request and response. Regardless of what the messaging, the actual request is, there's always a communication of request and response. So look, this is really advancing. So in the styles of communication, we have point-to-point, right? T0 to Tn. T1 represents a time point where after the client sends a message, it actually is received by the server, and between T1 and T2, server does some processing, and an acknowledgement is sent back. Or the server has received it, and the connection or the communication ends. Here, there's no communication, right? JMS or other things, that's just called a queue. You just drop a message on a queue, fire and forget. Request and response, similar to what we saw, T0 to T1, same sort of thing. T1 to T2, the server receives it, processes it, generates an acknowledgement, and from T3 to T4 sends it back. Now the key here, aside from the obvious client and server, we have our request, we have our response, but these blue arrows represent a really important thing, right? The communication channel. The only reason I highlight that is because in MQTT, it represents a persistent connection on both ends, right? So failing that persistent connection, you're going to have a broken connection, no communication, and a failed pattern. So request, callback, same sort of thing. Now, what's interesting, in this case, the initiating client and the responding client or the callback client don't have to be the same component or the same process, but they can be. And oftentimes in certain things they are. And then the last, I think this is the last one, the actor model. Right, everybody's familiar with reactive programming now and WebSockets and things like that. The actor model is just a mathematical model of concurrent computation, treats actors as universal primitives of concurrent computation. Nothing special, but the really nice thing with that is that you're folding an entire state and the entire communication of everything into one, I guess I want to say unit of work, but that's not even the right word. One abstraction that, in our case, would almost be a single callable. Now, the last one we're looking at is publish and subscribe. And the reason I left publish and subscribe last is because, similar to the callback model, we have a subscriber who subscribes to an endpoint. And in the case of MQTT, the endpoint is, I don't think I included a slide, unfortunately. Wow, what a mistake that was. It's / delimited, if you will. And they register with the publisher. And then they, in this case, the acknowledgement or the response contains subscription information that may or may not be stored by the subscriber. And the reason it's dotted is that, again, may or may not be received by the same subscriber. And what was interesting about that is yesterday in Michael's talk, they used a proxy to actually communicate between their subscriber and the broker to avoid the persistent connection between whatever mobile device or whatever tiny device they had, and then communicated with that proxy in order to handle the persistent connection. So you can assume a proxy in small embedded devices, like very small, tiny, like maybe your mobile phone or maybe even a heart sensor, for instance. It can't maintain a persistent connection to some server, in the cloud on its behalf. So it would proxy through something and then connect periodically in order to exchange state or communicate. So in this case, T0, obviously, T1 represents that first transmission. T2 is the receipt. And then T2 to T3 is the delay in whatever the publisher has to do and to connect, or create whatever response and subscription info it needs to. And then T4 represents that subscription being forwarded. Basic, but I want to make sure that we all talk about the same thing. So with enterprise messaging, right, we have a number of tools or a suite of tools that provide anything: business process orchestration, systems and data integration, monitoring, transformation and routing, logging, security, you name it, right? There's all these things. What's interesting about one of these points here, this transformation and routing, that's really kind of the canonical definition of what a broker is. There's other aspects to enterprise messaging as well around the systems and data integration and messaging and orchestration that provide a deeper, richer functionality. And with MQTT being a lightweight messaging protocol that actually exchanges in a binary format, you need to ask yourself, okay, if I wanted to bridge those two worlds, how could I do that? And we'll talk a little bit later about ways that you could actually transform or integrate MQTT with an enterprise system simply by mapping or translating and kind of, I don't want to use the word proxying, but we'll see different patterns later, or we'll talk about it at least. So then, again, all of the different technologies we talked about earlier, and most systems are not homogeneous. Who works with a single tool technology here? None of us, right? All right. So the architectural attributes of enterprise systems: highly available, fault tolerant, secure, redundant, reliable with delivery guarantee and retry, and message ordering. Now, there's one issue with MQTT. The protocol doesn't talk about message ordering. Matter of fact, it doesn't guarantee message ordering. It does talk about delivering messages in a guaranteed manner to the extent that you have certain things configured at the time you connect and establish a communication connection with the broker, but it doesn't guarantee message delivery. So with most brokers, with any broker, you're not going to get that unless you create some sort of extension or have some sort of extension, which is where you get into an issue of, okay, now you're outside the protocol, you're adding different functionality. So moving on, and then client session management. There is small session management that MQTT talks about, but it's very specific on what it manages, and it only manages a small amount of state. So getting to the protocol, so that's what it means. It's a pub sub message model, and it's standardized both in OASIS and ISO, lightweight, but it's got a constrained vocabulary. So if it was a DSL, it would be small enough to implement and easily consumable. So the protocol requirements is that integer data values 16 bits in big endian order. All text is UTF-8 in encoded strings. So you're transferring bytes. Clients have to send bytes. Broker receives bytes. Acknowledgements are in bytes. Everything's in bytes. Now that leads to a problem if you're trying to send a lot of data, because all strings are prefixed with a 2-byte length. And in UTF-8, strings are limited to 65, 535 bytes. Character data must be well-formed, and the null character is not permitted in string data. So you're not sending gigabytes of data across the network. That, unfortunately, is kind of a limitation, obviously, in enterprise messaging. So the question becomes, where would you use MQTT if you were going to use it as part of your messaging architecture in enterprise messaging? You might use it, say, as a small eventing, maybe a small notification system, or you might actually take and use different enterprise integration patterns with it. So for instance, rather than trying to transfer, the huge amounts of data, anything over 65K, for instance, that's a pretty limited amount. So take, for instance, if you're doing a regular integration pattern where you're transferring, for instance, say a small file that's, less than a meg, but say it's 600K. That's not unreasonable to transfer 600K across the wire. What is that? Let's make it 400K, so that's 100 packets. 100 packets isn't that much, right? But the problem is you can't send that. So what are you going to do? Send, that many messages? Problem is you can't link messages. So with regular patterns, you could do something along the lines of, rather than sending the large file, you could probably send in the payload maybe a file location or maybe an endpoint or something that then, goes to an endpoint consumer that then calls back, pulls that file down, and then continues processing as part of the the enterprise integration pattern. So you're limited to the amount of data you can send, but you're not limited based on your patterns. And for most people, if you've read Gregor Hope's book on enterprise integration patterns, there's a litany of things you can do to work around that. So moving on. So the message types, very, very simple, right? There's a connect, subscribe, and unsubscribe. And then for each of those, you have your corresponding acknowledgements. Publish, and then your publish release, publish complete, ping request, ping response, and disconnect. Now the key is when you're communicating between these two, client and server, or subscriber and publisher, how do you maintain that connection? And that's obviously where ping comes in, the ping request. So let's look at a couple of use cases, right? The Internet of Things is great because you have all these different devices. They can publish through the broker, through their various endpoints. You can have your thermostat publish to a point, say, thermostat is connected through your home, and maybe it's connected through home, convenience, comfort, and it says, okay, its message is too hot, or maybe it's cooling down and it says, okay, just right. So now maybe that, I'm not sure what that symbol is. Does anyone know? Give me a guess. A smartwatch? Really? That looks like what is that then? That's the smartwatch, right? Sending email. That's a female's watch. The other one's a male. Okay. All right. I'll go with that. Sorry? Smartphone. I know. Yeah, it was a neat symbol. I'm like, I'll put it on there. So you end up publishing through the endpoint. In this case, there might be something listening for that. Let's say it's this, whatever this is. It wants to know when the temperature reaches a certain point. It would subscribe to that particular endpoint in the broker that publishes to, picks up the message, and then would carry out some action, right? So publish, subscribe. It's basically an event notification system. And then you could have coordination within your house, right? The smart thing. TV turns on, the refrigerator opens, so you can go get your snack. Another interesting one, there's your enterprise architecture. Why couldn't you actually have part of your event notification system down in here, MQTT broker living? It's not too difficult, you could do it. So let's look at the use case. I've got about 30 minutes, maybe a little bit longer. That's a good point. So what I'm going to do, rather than go into all of the server design and stuff, I decided to focus on the connect, because the connect would give enough meat, I guess, to the design of the actual broker. And then we can get into how I would scale that broker if I was going to actually do something distributed with it. Sorry, when I actually do something distributed with it. So again, simple use case, right? It's connecting. We have our basic channel stuff to worry about. We have our subscriber, publisher, client, broker. And then from there, it's really what we care about. We have the transport connect that happens between the client, a network transport, and the broker. And that's not something we're going to see too much in terms of something we really care about. But when you're writing software, that's what you end up starting at. And then you have, very simply, your connect through the transport, and then the acknowledgement. So what does that lead to? Some basic abstractions. So here's, in MQTT, here's the header you end up sending, or the list of data. And I'll break it down. That's the header part. Type is the type of, that header is actually common across all of the connections. Type is only 4 bits long, and 1 refers to connect. I think 2 is connect ACK or something, and then publish, pub ACK, subscribe ACK, all of those things. And then this one here, it's not anything, it's reserved. And then length just refers to the remaining length of the message that is calculated. And then protocol, well, I'll advance it to the next part. And this is the variable header, where you end up sending the protocol, which is MQTT, the level, which is the version number. In this case, this is 3.11. The union here of the bits is the rules essentially around what is getting sent. So first bit is reserved. Clean session means that I'm starting with a new session, or I want to preserve my session. The will message just means I'm going to send you a message that lives down here that when I disconnect, you're going to send it back to me so that I can take some action, whether it be notifying something internally or I can do something with it. Quality of service is 2 bits, which just, it's 0, 1, or 2. And then will retain tells the broker, client tells the broker, I want you to retain that message in the session so that you do tell me. And then password and username, obviously, really, password and username are nothing more than flags that say, okay, I have a password username in the payload. Of this payload, client ID is the only one that's required, the rest are optional. Because you need to connect before you can subscribe to a topic, right? So that topic is just there, and it's not used. All right, so moving on, we're going to look at the flags and kind of go into a little more detail on what they mean, because there's several different rules. So clean session, 0, must resume communication based on current session. Will, if it's 1, connections accepted, a message must be stored, right? Just like I said, will, oops, sorry, wrong button. If will message is 0, will QoS, quality of service, must be 0. If will message is 1, QoS can be either 0, 1, or 2. And then will retain, broker should retain will message or not, 1 or 0. Password is present, username is present. What's interesting, must not be present. They use must a lot, meaning that you clearly, you can't interpret it any other way, it just must. And then your CONACT is just basic. The only thing you care about are session and return code. And those are the return codes, just basic stuff. So looking at the component design on the preliminaries, so I tried to use templates a lot, because we're supposed to. I used policy-based design, similar to what was recommended in Andre's book. That's a great design technique. I don't use as much template metaprogramming as others do, but I do use a bit of it. And then the implementation is based on first principles, meaning that I didn't use Boost ASIO library, whereas others would have thought I would. And it's just implemented as a single daemon on Linux. Now, the trick here is not a trick, sorry, kind of a poor choice of words. With daemons on Linux, you can run more than one, but with MQTT, it's the protocol and the standard require a very specific port, and you can't run, obviously, on the same port. So it's one and done on the host. And then for me, this was just a personal research project exploring MQTT. Again, there wasn't any goals around providing distributed semantics to this. Again, that was another project, and I do have several policies that I can actually now fold into it, should I want those. So where I started, we can ignore configuration and logging. I mean, I did do some state management around session. The interesting thing is, started a design around rules involving the use of predicates, and where I was going with that was I wanted to do variadic templates with predicates, and I thought it would be really cool if you could create a set of predicates rolled up as a set of variadic templates and then just do an apply on them. And I got close, but I didn't really have enough time to wrap it up, and so it kind of left that implementation off. And then the process scaling simply just means, I was using thread pooling and package tasks as a way to handle a little bit of scaling inside the server. And then, response handling, channel communications, and request processing, all within the broker. The broker runs as a single process. So the details around that, apologize for how this slide is laid out. Really, I'm just showing a class for the broker that derives from a basic daemon. And that daemon actually has a network policy, and it takes another handle, an acceptor, which is, again, a template parameter of an accept that takes an opaque handle. So it kind of builds on itself. And the daemon itself is actually a little more involved. So the daemon takes a number of policies, but most of them are defaults. So there's a daemon policy, and the idea with that daemon policy is that you could instantiate a daemon on other platforms as well by parameterizing the policy, the signal handler, and then just in this case I defaulted for exception handling to throw runtime error. And then instantiating the broker, it's pretty straightforward, right? You read some configuration, set it up. The handles type just an opaque, well, it's not opaque, it's a specific type. Server name, you set up the port, call start. It gets interesting when after that, what happens after start. So in the Linux daemon, this is from Michael Karras' book, Linux Programming Interface. I just wanted to make sure that everybody understood creating daemons. I don't know if anybody does that, writes this stuff for themselves. But the nice thing is with creating a daemon, simply call fork, and that actually just basically kills your parent, makes you a child process of the init process. And from there, you actually call set session ID to give you a new session, obviously exit if it returns -1. And as a convenient shortcut, calling fork again actually does a bunch of extra work behind the scenes. And it relieves you of the burden of having to do a bunch of stuff on Linux. And you clear the UMask, set the working directory to root, clear some file descriptors. Careful if you've got a logging framework that uses file descriptors. That's a fun one. And then you use dub2 to reopen standard out, standard error to dev null. And then so the networking service, if you remember, that was the policy for the basic daemon Now remember, we had the transport layer, and this is kind of what this acts as. You'll see the network service is parameterized with a socket lifecycle, that takes an accept, but it takes an accept service descriptor, and it derives from them. Now the key is when you call start is delegated to by the daemon and determines if it's listening on that socket, connects to it, listens, and then sets up for an accept, right? And the accept is what reads or waits for connections. So that wait for connection, real straightforward. So it's an internal override. It just loops forever, calls receive on itself, and it gets a handle back. If the handle's good and it's enabled reading on it, or if it doesn't enable reading, we have a problem. Otherwise, some magic happens, and it's not really magic because here it is. The handler is called handle on that, and it creates a response strategy. And really what that response strategy does is nothing more than allow for the exchange to occur, to be created. And that buffer that gets created from the message to the exchange eventually ends up being part of this task and submitted to a pool, which is a thread pool for work. So all in all, the server just gets a connect in, builds the message, whatever type of message it is, based on an exchange, submits it to the pool. And that's really what the broker does. Now the key to the broker being able to enforce all its rules and handle its status changes, if you will, is the on status change. So the broker passes this instance in of itself on the exchange, and you'll see how the exchange does callbacks as it progresses through its life cycle. So what's an exchange? It has a state, created, running, stopped, blocked, canceled, finished, and there's a proceed. You can get the status, you can set the status. You notice in a minute why. And then you can also get the configuration and set the configuration. Now, this is really an abstract interface. And really in the exchange, it starts the task. The exchange state is transitioned from created to in progress, and the event callback occurs on the broker. The broker receives a non-const reference to that exchange. And then depending on what type of exchange that is, again, we're going to have a connect exchange, a subscribe exchange, publish exchange, and various acts, because the exchange is the one that communicates with the client and does connection cleanup at the end, and it notifies the broker. So it knows, based on its type, what rules it needs to enforce. So again, while not completely isolated like an actor, it's encapsulated enough that it manages enough of its state that it's independent. Oh wow, that's the last slide. So the point with that, and where I would go with that, because again, you have this state, if you will, in the exchange. And it handles, or it operates independently in a separate thread. The only, with the connection, so if you look at the messaging, and let's talk about the distribution part, right? So how would I distribute this as a system? The first thing I'm thinking right now is a single broker would handle, you could do several things. You could configure this broker to handle only connections. Then you could have a separate broker that manages state for those connections. And you could configure multiple publishers to handle, again, the communication layer of publishing, sending and receiving, and even subscriptions. So you would distribute the work of breaking up a broker into multiple, I guess, not processes, but by the phases, if you will, and do that. But the problem I see with that is that given the size of the communication, that you're not going to have a lot of pending work being done and not a lot of, like you'd be connection, I think you'd be more connection bound than anything. So you'd probably just scale the connections with a proxy server in front of that even and get around that. But at any rate, I'm not really sure. So, I mean, we're a little early, but I thought I'd open it up to questions.
So a lot of things described here have been implemented in 0MQ, non-MSG, gRPC, that all of them has wide community support and well debugged. What was the driving force for choosing MQTT in the first place?
I'm sorry, I missed that last part. What was the driving force?
What was the driving force for choosing MQTT as opposed to other like gRPC or 0MQ in the first place?
Excellent question. So the question was, a lot of these concepts and things have already been implemented in 0MQ and RabbitMQ and any of the other MQs already. So what was the driving force in implementing this in MQTT? It's a good question. For me, it was mostly to explore MQTT. It wasn't, hey, I'm going to build a better mousetrap. It was a lightweight protocol. Ultimately, what I'd like to do is be able to scale this down to embedded devices and actually distribute those embedded devices and see how I could actually get multiple devices to work together. That's really all it, it's mostly selfishly motivated. RabbitMQ and a JVM, or even working with other heavier products that require more memory, you're not going to really be able to do that. So it was just mostly kind of a research project on my own. Yes?
So let me ask about MQTT and message format. So you mentioned the limit size of string is 65 kilobytes, but the payload is not. So I mean the payload is 260 megabytes is allowed. So your broker treats that payload well.
Mm-hmm. Yes. So the broker right now, sorry, let me repeat the question. So the question was, the limit size of the message is 65K, but the payload limit is 260 megabytes, you said?
Yes.
So how does your broker treat the payload size? Does it treat it well? Right now, right now, I haven't pushed it to the point where I have exceeded multiple clients, pushing that much data through it. So I can't really say, it scales really well, because that's a performance test that I just haven't run on it. But I can't really say it treats it well or not, so I haven't done that. But theoretically, it's going to fall over at some point. I'm going to have to bleed off some of that work to something else, and that's either be some sort of distributed workers or something that handle that work, just file readers or file writers or something that's proxied somewhere else. Yes.
What strategy do you use for packaging tasks and
Excellent. So what is the strategy I use for packaging tasks and thread pool? So I have a thread pool that I've written that's just a regular thread pool. And I just use regular package tasks. That was a kind of a definition, like a using clause that I was showing. And I just move the actual, oh, sorry, let me back up. So in the thread pool, it's got a template parameter it accepts. And so I'm passing in the actual package task as that, and then as a callable. So I've wrapped it into a callable. And from that callable, when I move that into the thread pool, when it's ready for work, the wrapper function that package task is in then handles calling the package task and waiting for the result. Again, keeping in mind that there's callbacks, right, in the exchange that occur after that happens.
What is the average performance of such a system? For example, if you had two clients and one broker in the terms of message per second?
I haven't done a performance test. Like two clients, it depends on the size of the message and what they're doing, right?
Maybe empty message.
Pardon me?
Empty message.
An MQ message?
Empty.
Empty message.
Without any data.
Or you're thinking deadlock, is that what you're suggesting? Because that was about the only thing I could think of like, that you'd be worried about. But that right there wasn't the exact, that didn't include the locking code I have. So there are two different locks in two different scopes, right? There's a submission lock that is different than the actual lock that wraps the receipt of it and the reading of the data. So they occur in two different locks and they don't cross, if you will. I don't know if that's right. They don't overlap, I guess is the right term. Yeah, I mean, empty message and two clients, you're thinking deadlock.
I was interested about the performance because you can compare different brokers using such a values.
Right.
How many messages it can process? 1 million per second, 1,000 per second.
Right, and again, I'm not doing performance at this point. I only started this in June, so it's only been a few months. You know, maybe next year at this time, maybe I'll have, well, I definitely will have if I keep up with it. So I have plans, again, there's a schedule I have between now and C++ now of what I'm doing in conversion and stuff and project plans, so. Yeah. Anyone else? Yes.
In the early slide, you had the next struct, and it seems to be a mixture of a header, but yet had other fields in there.
It did, yeah.
Kind of confusing. It wasn't purely a header.
Well, it's part of the MQTT spec. Oh, sorry, let me repeat the question. So in the earlier slides, I had a struct for the connect, and in the header that I identified, there was not only just header data, but there was other stuff. So the specification talks about a canonical format. So there's a fixed header, a variable header, and then the payload, and that's in all messages. And in the case of the connect, it's very specific. Well, in all of the messages, very specific of the format and the types of data that go in each. And for the connect header, the initial, sorry, I'm just thinking big endian versus the little endian. I'm just trying to, the type is the most significant bits, requires 4. And then there's another least significant bits are reserved. And then the next byte is the remaining length. And then after that, I can't remember off the top of my head, there was something else. But that was kind of what I tried depicting in that struct. So it is according to the spec based on how it is. And then in the make message function that I have, the template function, I go through and actually build the message correctly, byte by byte, according to the spec and how it's laid out. I'm not sure if that answers your question, but there are certain reserved, bits, and there is a strict format on how the bytes align and lay out. So it is to match with that, though not in the exact bit format. So those watching at home with the spec open, don't scream bloody murder, because there is byte manipulation that happens in the make message. So does that answer your question? And I can show you more after if you want. Anyone else? Okay, thank you.